Good morning, good afternoon, depending on where you are. Tiago Filomena. We will be presenting today this webinar. We'll be discussing financial optimization problems with Gurobi. I'll be presenting with Marcelo Perlin and Marcelo Teixeira this webinar. Just to give a brief agenda on our presentation, I'm going to start with some introduction on portfolio optimization. Then Perlin he's going to give like an example on passive investing. And this example is more, the idea is to discuss a little bit more about modeling with Gurobi and computational issues. And then we're going to have Marcelo Teixeira talking about an example that we chose because it's not a common example to see. It's a hedge of a banking book, a hedge of a credit banking book of a retail bank. And this is going to be the three topics we will discuss today. So first, like a brief introduction of Finor. Our name, it's really related to the presentation we'll have today. Fin comes from finance and OR comes from operational research. That's where the name comes, the Finor name. We are a company that we develop algorithms for finance and from finance. And a lot of people in the company has operational research background. So we really focus on computational methods for finance. We solve problems such as risk management, portfolio optimization, credit scoring, pricing, and some other problems. We really focus on this integration of tech and finance. Here, just the three main verticals that the three main deliverables that we do at Finor. We solve some complex financial calculations, such as matching a complex cash flow in a network economics problem. We work a lot with AI, machine learning in problems for credit, fraud, and pricing. And today we will be discussing mathematical optimization that is used in portfolio, ALM, and index tracking. We'll be showing an index tracking and ALM example today. And all the solutions we develop on mathematical optimization, it's always on the Gurobi solver. So we always use the Gurobi solver to solve our mathematical optimization consulting projects. Here, just to kick off, we'll be talking about this interface of finance and OR during this presentation. And it's good to go back a little bit and see like two of the superstars of each of those areas. You get Danzig and Markowitz, which have a long time relationship, I would say. There is a paper on operational research from Informs from 2002, a small note that Markowitz wrote, mentioning how Danzig influenced like the solutions he proposed for the modern portfolio optimization. And with that in mind, I just would like to point out when we are discussing this portfolio optimization problems, we are always discussing a problem that is in the interface between many areas. So we have OR, we have econometrics, but we have a lot of tech on that because we got to put those models into production. So we got a lot of data engineering and ops to that. And also, like, we should never forget all the financial intuition that you need to solve those kinds of problems. Without that, it becomes just like might become just a math competition, you know. So here, it's just our personal view, you know, it's not like any academic statement, stuff like that. But with our experience, we would say that there are some practical aspects that OR brings a lot to the portfolio optimization area. The first one, I would say that's the model size. These days, we have like the financial markets fully integrated. So a hedge fund can buy assets all over the world. And we in developed markets or emerging markets, and with many asset classes and thousands of assets. So we can also say, I almost say that you got an infinite possibilities on the asset side. Furthermore, I think that one thing that the WAR community brings a lot to this problem, it's the modeling constraints. So every portfolio manager or trader, you gotta respect a lot of the regulatory, trading, and managerial policies. It's not just like optimizing a model without considering all the regulatory and trading constraints that you have in your system. And those constraints also can increase a lot the complexity of the problem. So the discussion we'll have today will have a lot of relation with model size and the constraints you have on portfolio optimization. Just to give I think that's we're not gonna go over much math in this presentation, and just a portfolio optimization problem. In general, we're gonna be maximize or minimizing some function that can be linear or non-linear, and it's going to be subject to some constraints that also can be linear or non-linear. And we'll be, in general, dealing with continuous and integer variables at the same time. So this is just like a general structure that we'll be solving when we are dealing with portfolio optimization problems. A general structure of a problem will be minimizing, for instance, some risk metric, such as a variance, the value at risk, or CVAR, or some other risk metric. We might be, for instance, trying to minimize some transaction costs. In a passive investing problem, it's common to try to minimize the tracking error, or like in a hedge operation, we might be trying to minimize the duration gap of the portfolio. We also might be maximizing some functions, for instance, some long-term wealth or return. And one thing that we should have in mind that in general, we'll have a nonlinear objective function that's very often quadratic, especially when we are talking about a risk metric for our problem. And like a nonlinear function, it's hard. In general, it's harder to be solved than a linear function. Going a little bit on the constraints, and I would like to point out that constraints on the mathematical problem, it's like translating some qualitative or intuition to the problem. So we are many times with constraints, we are trying to translate trading or regulatory or some managerial policy to have that online model on the problem. So just some examples, for instance, you might got like a liquidity constraint, especially when we are dealing with assets that are not traded as often, and those constraints might be represented by a market impact or like the liquidity availability. You might have some managerial preference that many times are related to the policy of the fund that you're managing. For instance, you might have bounds on the weights of some assets. You might have a long-only allocation, for instance. You might have a limited exposure for some segments or some countries. And you have a lot of regulatory constraints also. So all these qualitative policies, I would call them, when we translate that to the mathematical model, the modeling of that can be based on linear functions, non-linear, that can be quadratic or non-quadratic. But very often when we add those policies to our models, in general, we'll be dealing with integer variables together. And then we all know that when we are dealing with integer variable, we'll be dealing with problems that have a higher mathematical complexity than when we are dealing with just continuous variables. If you want to see a little bit more about that, there is this good paper from Como, Tucuncu, and Fabozzi, the George 2014 paper that talks about it. So the structure of the optimization model, we're going to have like objective function subject to some constraints. So let's say in general, in finance, we'll be talking to a quadratic objective functions with linear constraints maybe, and then variables that can be continuous and integer or binary at the same time. This can be, this will yield to a MI-NLP, a mixed integer nonlinear programming, sometimes you might have a fully linear problem that can be a MIP, a mixed integer programming. And I think that this is the importance of be dealing with a solver such as Gurobi, which is pretty general in the types of problems that it can solve, So you don't need to be that worried that if Gurobi is gonna be able to solve or not this type of problem, given that it's pretty general on the problems that it solves. So we'll be dealing with more complex mathematical problems, and then in general, in finance these days, we'll be dealing with large-scale optimization. Given the number of assets that I have already talked about it, we have a fully integrated financial markets with thousands of assets. If you take just like the number of stocks that you have available at New York Stock Exchange and NASDAQ, we're going to be talking about thousands of stocks. And we all know that when we increase a lot the number of variables, we'll be, in general, increasing the complexity of the solution also of solving this problem. With that, we have all the boon in algorithm trading that can be related to tradings in high frequency, in medium frequency, or some lower frequency. But we'll be always demanding computational performance of that, or for trading, or for back testing, for instance. You cannot wait 2-3 days to back test a model these days. So this is another thing that Gurobi helped us a lot when we do some projects, that its performance, it's the best in the market, and computational time matters in this business. In portfolio optimization, we'll be dealing with large-scale models with reasonable complexity in terms of its mathematical structure, and will demand fast computing. So this is pretty much what we will be talking today on the way we model our problems over the Gurobi platform. And just to finish again, here I give some very few examples of portfolio optimization problems, such as some active investing examples, such as the first one that people in generally you see in the literature, the mean variance. You get all this trend on the minimum variance portfolios, given that you have a lot of estimation risk on the returns. So we got all this risk parity literature right now. Also, you have all the passive investing strategies that we'll be talking these days in this presentation, and some ALM cases, which is the most used one is the pension fund allocation. Then we decided to present in a banking ALM today, which it's harder to find material on that. And then again, just like to wrap it up, it's a really interdisciplinary problem. So think about that, all this cloud and engineering and ops, it's pretty hard to do. Sometimes we gotta have like a lot of finance intuition on what we are doing. And of course that we gotta be integrating on the OR and econometrics to all of that. With that, I'll stop here my part, and Marcelo Perlin is gonna start.
Thank you, Thiago, for the introduction. Okay, so in my part of the presentation, I'm going to go deeper on the topic of index tracking. So, as a very brief introduction to the issue, one of the motivations for index tracking and the reason why it became such a popular problem in optimization is because passive investing became very popular in the last decade, right? So passive investing is basically you buy some diversified portfolio with, let's say, 100, 200 stocks, and basically just sit on it, right? So this is very different from an active investing, where you are actively trading stocks. So you have to study the companies, you have to understand the business, and so on. But for passive investing, since you have such a large number of stocks in your portfolio, you basically don't have to do anything. That's one of the reasons why it became so popular, right? So you just buy the index and then you just sit on it and you wait, let time do its work. And the good news is that historically, this has done very well for anyone that is following that strategy, okay? So why does it matter? Well, it's very simple. If you buy in the index, one of the things you have to understand about financial markets is that these indices, they are all theoretical, right? They are not actual, it's not something you can go in and trade the actual index. So they're just theoretical indices, which are composed by individual stocks. So if you want to have the index, so let's say you want to have an S&P 500 in your portfolio, what you can do is you can just buy the individual assets following the compositions that they have on the market index. So for example, Apple is around 7%. You can see that on this table I'm showing on the slides. Microsoft's around 6% of the S&P 500, and so on and so forth. So if you want to replicate the index, what you can do is just, let's say you have $100,000, then you just split it according to these weights, okay? So what's the issue? Well, it's very simple. I mean, 500 stocks, there are a lot of stocks to trade. And also you have to remember that the indices, usually they are rebalanced quarterly. So this basically means that every 3 months, you have to buy and sell, stocks in your portfolio in order to keep the same composition. So index tracking, it's a smarter way of doing that. So the idea behind index tracking is to replicate a market index, but using a much smaller group of stocks. So one of the things we know about financial markets and properties of financial return is that they are highly correlated. So instead of having a portfolio with 500 stocks, you can probably do it with the same performance. It's not going to be equal, of course. It's not going to be symmetric, but it's going to be very close by just using, let's say, 30 stocks, 50 stocks, and so on, right? So what's the gain? Well, very simple. If you trade less, then you're going to have a lower trading cost. Every time you trade in financial markets, you pay a fixed fee, like the exchange fee. Here in Brazil, we call it emolumentos. I'm not sure about the name, but just a trading fee from the exchange. And also you have some implicit costs, which are the liquidity costs. So if you have to trade a less liquid stock, then you're probably going to have worse prices, right? Because you're always trading in the trading book. And if you're buying, you're paying for the ask price. And if you're selling, you're basically saying at the bid price. And you're always paying for the spread, right? So overall, the rule is quite simple. The less you trade, the less cost you have to maintain your portfolio. And not only that, another reason why index tracking is so popular as a problem is because you can have some regulatory issues. So let's say you are a pension fund, and as a pension fund, you can cap the weight you have on individual assets. You can say, well, I don't want more than 5% of my portfolio on any individual asset. And also I don't want more than a particular sector, let's say utilities. I don't want it to be more than 20% as the sum of the individual assets. So you can do all these things mathematically, and this is quite easy to achieve when you use optimization. Liquidity constraints, as I said, this creates costs for trading, market volatility as well. Usually you avoid those highly volatile stocks because they basically increase your tracking error, and you don't want that. So every time there's a shock on these volatile stocks, you're gonna do worse in terms of tracking. And also computations limitation, right? This is something that's I'm going to show you in a couple of minutes, but once you start, as Thiago has mentioned, once you start to increase the number of assets in your portfolio, it gets really tough to solve it using computers. Okay, so right now this is the math part, right? So this is the actual formulation that we solve in this presentation. I'm not going to go deep on it, okay? I'm just gonna skip through, but basically the most important parts are the objective function. So you can see we're minimizing tracking error. And within this tracking error, we have two variables. We have WI, which is the weight of asset I in the tracking portfolio. And also we have ZI, which is a binary variable, 0 and 1 for asset Y. So the weights are just like from 0 to 1. So it can be like 10%, 20%, and so on. And this auxiliary variable, which you call ZI, it can only go from 0 or 1. It's binary. And also we set a constraint that the model will have to choose which assets will include in the optimization. So we do that by just looking at this restriction here where WI has to be lower or equal than ZI. So basically when ZI is 0, then WI has to be 0. And when ZI is 1, then WI is more flexible. It can be from 0 to 100%. And later, we also set exogenously the value of K, and K is the maximum number of assets we want in our portfolio. So we just restrict ZI by saying, well, I want the sum of ZI to be lower or equal than K. Okay, so let's see an application. So in this presentation, we wrote some Python code for using Gurobi. If you are not aware, but Gurobi has many APIs, so you can call it, you can call it using R, you can call it using Julia or Python. Python is a very popular programming language, especially in data science, which is one of the reasons why we use it. And in this example, this first example is basically a set of steps for a data science project. The code will import data from Yahoo Finance, we'll prepare it, we'll clean it up, right? Removing stocks, they don't have enough data. It sets up an optimization problem with Gurobi. It solves it, and then it analyzes the results, right? And this code is free. It's available on Colab. So Colab, it basically means you can run this code on your browser. And I'm actually going to put the link here so anyone can have a look. Okay, so this is like a gift to you guys, okay? The code is heavily commented. It does 2 types of index tracking models. Unfortunately, I would love to go through this code with you guys, but then we have to spend a lot of time here and really don't have it today, okay? So I'm just gonna skip through the next session. Okay, so this code here that we wrote, this is a very nice example of using Gurobi. It's heavily commented. However, this is just like a toy example, right? This is not usually the way that we do it in practice. We set up a team here in the company. We decided, well, let's look at this problem and solve it using proper tools. And one of these tools that we do is we actually use cross-validation on the data. So the previous example, this Colab code was basically just like you have a group of data, you have a time frame from 2015 to 2022, and then you just break it down in 2 parts, right? You have an estimation part, and then you have the testing part. But in practice, we actually do this exercise more often. This is a concept called cross-validation. It comes from machine learning. So basically, you break the estimation in many stages, right? So it's one way of simulating and saying, well, if I have this index portfolio, I'm probably going to change the weights of it. I'm going to re-optimize it very often, right? Because even the index, as I mentioned, changes quarterly. So in this case, we rebalance the portfolio 11 times. So the data is from 2015, 2022, as I mentioned. And for each blue vertical line you're seeing in this top right plot, we're going to re-estimate our optimization model. And on the bottom right, you'll see that this is one way of looking how we organize the training and testing chunks of data. So on the vertical axis, we have the fold number. This is 11. It starts from 0 and it goes to 10. Okay, this is just because Python starts indexing from 0. And the blue line is the estimation part, and the orange line is going to be the testing part. So we use this chunk of data to estimate, and then we test it. We use the chunk of data for chunk 1, and then we test, and we do so 11 times, right? This is how we did for the results that I'm going to show you right now. Okay, so this was nice, and once we start writing the code and executing, one of the surprises, well, we're not surprised, but one of the issues that we had is that when we had a k equals higher than 5 for n equals to 97, our code just didn't run, right? So we had a very nice local computer here, 16 cores, 16 gigabytes. It's very good. It worked for almost all projects, but it just you took ages and it did not reach a conversion. So this was one of the issues that we found in this project. But the nice thing about it is that even though we could not reach a convergence of the Gurobi algorithm, right, because the problem was so large, it's a combinations problem, it gets really big and very complex. When you look at the actual results from the first iterations, because when you use Gurobi, you set a time limit for the execution, right? So let's say half an hour, 1 hour, or so on. When you look at these results, even for running like 20 minutes for each fold, they were quite good. So this is a very nice aspect of Gurobi, that even though we didn't put any heuristics, we just used the default parameters of Gurobi, it actually started in a very nice location of the solution space. And when you look at the actual results out of sample, we see that the tracking errors are quite small. So this was a very nice surprise for using Gurobi. Okay, so we realized very soon, okay, this is for a desktop computer, will not work. That's when we set up a team and say, well, let's solve this problem by just throwing money at it. Okay, so what did we do? Well, first of all, we use heuristics. So heuristics is like a way to try to decrease the complexity of the problem. Usually, we do this when we really understand the problem and try to solve it. And for this particular case of index tracking, what we did is, the actual solution is available on the internet for, n assets. So the composition of, let's say, SP100 is publicly available. You can get the weights on the internet, like I showed for the S&P 500. So what it did first was to decrease the number of available assets. The intuition is, well, out of 97, we just use 50 assets, and we use the 50th with the highest weights. So the intuition is, well, if you go from 50 to 60, the individual weight is going to be much lower. So the likelihood of these assets getting into the solution is actually quite small. So we're just going to decrease the search space for this problem. Also, we use a warm start strategy by looking again at the K assets that have higher weight, and then just optimizing those in an unconstrained optimization. Just let the sum of W equals to 1, and then we use those as starting parameters for the algorithm. And not only that, but we also scaled up our computing resources by using the cloud, right? So this was a very nice solution, and it works perfectly. So instead of trying to run in my local desktop computer, we just let it run on cloud servers, which is faster, and also you can run concurrently. So you can feed a different part of the data to different servers and let them solve it. This is increase the processing speed a lot. And here I have a table of the instance that we used. So this is from AWS, from Amazon. Okay, so we have the name of the instance. Here I have the cost. As you can see, today these cloud resources are very cheap. So the most expensive machine is around $4 an hour. But at the same time, you have 72 vCores and you have 144 of RAM. So if you work with computers, this is a very heavy machine. You can do a lot of stuff with it. Okay. Okay, so what's the strategy? Well, we just wrote a Python script, a single Python script that basically just distributes all the problems to different instances. So this Python script would create 11 instances of servers in AWS. And for each of those, we just feed it with the fold that we want to solve the optimization problem, right? So this means that, when I run my Python code, 11 servers in AWS is going to solve my problem, right? So I just keep, in my computer, just waiting for the results and getting the status of how it's doing. And for each instance, once it finished, it just dumps a CSV file with the results, and then I just incorporate them all together and aggregate all the results in a single file, which I use to analyze our results. So, in the end, this is the nice thing, we were having so much trouble running this in a local computer, but when you go to the cloud, basically we ran everything. I mean, 4 values of K, 2 server types, 11 folds in around just 20 minutes. So this was really amazing result. And one of the reasons why I believe that, right, that, I truly believe that cloud is the key, is the future, right? If you want to solve these problems, it's much easier just set up a cloud infrastructure and let the computers run in some cloud in Europe or US and just get back the results. And likewise, the cost to do this was just $20, right? So this also includes some overheads, right? This is the actual, we got this from the budget from AWS. So, this was exactly the price we paid just to run this exercise, including the overheads of creating instances and so on. And these are the results. I'm going to go very quickly on them. So first of all, we have the runtime. We have three values of k equals 5, 10, and 15. We also have two instances here, 32 vcores and 72. As you can see, for k equals 10, when you have more instances of vcores, it gets lower runtime, of course, because Gurobi uses up to 32 cores in its estimation. When you have k equals 15, the problem gets a little more complicated, and then you'll see that we put a cap here on running time on 20 minutes, and most of the cases you actually finish the optimization, but some cases we still got the time limit. And for the tracking error, which is what motivates us, the real, the main results of this, as you can see that as we increase the value of k, you get lower and lower tracking error out of sample, right? So for k equals 15, you actually get a very nice tracking error of around 2 basis points. So this is quite nice. And these are the returns for our results. So basically, you just keep filtering the weights, right? And you do this for all points in time. As you can see, as times go by, here I have a plot for each year and for 2 different values of k. As times go by, sometimes the gap gets wider. It's because any permanent shock, in the index portfolio, you actually get some and it gets accumulated over time. But we feel these results are quite nice, quite reasonable for what we're trying to do. And what do we learn from this, right? So what are the key messages that we want to portray here? So first of all, solving this asset constraint index problem can be very tough. As we just mentioned, we had a lot of trouble trying to run this locally. So one of the reasons why we were able to solve it is because we went to the clouds, and also because of Gurobi as well, because it's quite fast and it runs very well. It has a very nice default heuristic for the starting parameters and the starting solution space. And also, just to wrap it up, we discussed internally, well, how can we improve this code, right? So if we instead of having just 2 weeks to do this code, if you had, let's say, 3 months or 6 months, which is the usual case of a formal project, well, first of all, you will use cloud batch services. So AWS and Azure, they have native service for this type of problem. So if you want, just rent a server to solve a computational issue, they have a very specific server for that, and they have some advantages on using this. Also, Docker containers, this is standard in industry. If you have any system on production, then it's very likely that you're using Dockers. For this case, we are not sure if the performance would be good because, Docker, they have some overhead. So when you have this computational problem with lots of computational requirements, this could be an issue. Also, cloud storage for sure. In this case, we use a SSH tunnel to send and retrieve files, and this was not stable, and it didn't work sometimes. And we know that we could do the same using cloud storage, like a blob container on AWS or a container on Azure. This works perfectly. It will be very nice to have it. And also, this is just one of the things we realize, well, this is just a predictive problem, and all the machine learning tools for monitoring models and data, they could be used here. So Airflow could be used here, MLflow could be used here, just the data pipeline. This would be very easy to set up. And to end it up, we also feel that tracking results and monitoring the weights and the tracking over time will be a very nice thing to have in a production environment. Okay, from my part, that's it. Thank you very much. And now I leave my presentation to my colleague, Marcelo.
basically, I'm going to be presenting to you a problem that has a little bit of an analogy to what Dr. Perlin presented now, which is about using how to use an optimizer tool. In his case was to reduce a large portfolio stocks into only a few of them. In my case, I'll be talking about how to do the same for thousands of fixed income securities and represent their risk with only a few interest rate futures contracts. And through the process, we'll show this hedge will still obtain a very good results in terms of dampening the volatility of the portfolio, hence protecting a bank's balance sheet. So the key point here again is how to deal with thousands and thousands of loans, which no spreadsheet can handle, and transform this whole banking book into risk buckets so we can deal with them in a very neat way. And I'd like to say that Finor will actually use the same computing language and code to actually read the data from the bank and do all this transformation in a seamless environment. So to start the presentation, I'd say this presentation is very timely because, as you can see, inflation has been going up throughout the world, both in the developed world and as the developing world also. And for reasons we won't cover here, but as a consequence, central banks have taken notice and they have acknowledged the need to change monetary policy in the direction of raising interest rates. And when this happens, it's a big challenge for banks because it makes them vulnerable in the sense that they generally finance themselves with short-term floating rates, such as demand deposits that could be enticed to flee to interest-bearing accounts, or they use short-term CDs, which they need to roll continuously. And as interest rates are going higher, they will have to roll ever more expensively to fund their short to to long, medium-term fixed rate loans. So as interest rates rise, what happens is you're discounting future cash flows. So the higher the interest rate, the higher your discount rate to bring this cash flow in the future to the present. So therefore, fixed rate credit portfolio would see the present value of their loans going down, hence putting the net interest rate income of the bank at peril. As you see, the spreads will narrow when the short-term funding will get more expensive, while your fixed rate assets will actually lose value. So one way to protect this, the bank, would be to short interest rate futures contracts, which make this institution long interest rates. That is, the hedges would actually go up as interest rates go up, therefore providing an offset to your credit portfolio loss. So in this picture now that I'm depicting, it's a simple zero coupon bond. That is a bond that you get paid the par value, in this case 1,000 in the when the bond matures, and you pay the present value today of the interest rate that you're trying to discount. So as you can see, the green line, the 30-year bond, is both more sensitive to falling interest rates, as well as exhibits some different slope. It's a very sensitive to interest rates, so it's more sensitive, and the slope is changing also, which we call this the first derivative to this price function. We call it duration, which could be geometrical tangent of this line. So for small rate moves, the duration approximates well. And for bigger rate moves, as you can see, the slope will be changing. So we use convexity, which is another measure, is the rate at which the second derivative, the rate at which the duration changes. So basically, like for you, the not financially savvy, just take my word, the longer the bond, the longer the duration, more convexity has, and more interest rate volatility risk. So that poses a problem. So when you have several cash flows, you need to decide how to hedge, because you can actually trade a whole bunch of contracts throughout the yield curve, which is this term structure of interest rates. That's what I'm showing here, how the interest rates on the left side change according to the maturity of your security. So that's the periods in days, interest rates. So a typical yield curve has short rates lower and long rates higher. But as you can see in this example, as a change from the orange line to the blue line, you can see the rates throughout the curve don't change in tandem. You can see that at this time, the Brazilian interest rate curve moved at the time the central bank was cutting rates to stimulate the economy as inflation was historically low. So if you had long-term loans, you would see the interest rate rise. You would lose on them if you only had interest rate long-term loans. If you had short-term loans, you actually would have gained. So what to do? You need to choose the hedges. So basically, we divide this problem into like 4 parts. First, we partition the yield curve based on key rate buckets spread throughout the curve. Then we calculate the dollar duration, dollar convexity, or each bucket along this curve, this partition. And for that, we took into account also to trade the hedges, liquidity requirements on the hedging instruments we're going to choose. And we try to minimize costs, that is, minimize operational complexity by not trading too many contracts and making this a nightmare for a trading desk. So to explain the problem again, once you have many key rates along the yield curve, you have to deal with liquidity and operational costs. And you shouldn't have a trade desk rely on many non-liquid derivatives. You create problems with that, and also not trade too many instruments. So Finor, using Gurobi as a solver, can help your bank by creating a hedging strategy. Will take account all of that while also achieving a very optimal hedge efficiency. So to be clear, in terms of mathematical problem, we have the objective of hedging the market risks, that is, immunize the portfolio to interest rates, while minimizing the operation costs, that is, not trading too many contracts, making sure all the contracts traded will meet liquidity requirements, so we are not trying to affect the market as we trade, and also trying to guarantee the hedge will be effective. So that's a typical mixed integer program that Dr. Thiago Filomena mentioned in the beginning of the presentation. And Gurobi actually helped us quite a bit on doing that. So just to show what we did, this could be any credit portfolio. You can see each bar, each blue bar is a cash flow, and you have thousands of them. In the case, I think we use 200,000 cash flow. So it's quite a problem to solve. So we use a code to actually translate all those cash flows into their risk. So as you can see, the cash flows, you can see them represented in the left-hand y-axis in blue. And the risk to each segment of the yield curve is represented by those orange bars, which calculate the dollar duration or each partition of the yield curve, which represent, you can see on the right y-axis in orange, represent the change on the portfolio by 1% change in the interest rate. And we inverse side. So now we show the results. We pick the time, a real time period, and we ran this solution to see how the hedge would perform. So you can see in green, that would be the money you would get paid or have to pay in terms of margin, daily margin on the futures exchange. So the money you're receiving or paying. And on the orange would be the portfolio value changes. And you can see that pretty much they are offsetting each other. And you will see actually right now more clearly. This is the net of the change on the portfolio value with the margins that you either paid or received. You can see it's very low. And in the next slide, now you're seeing how Gurobi actually chose the contracts for us, and also how they met the liquidity threshold. And you can see if you if you were to play around with the liquidity threshold, depending the size that you need to trade, you can see that you can find different solutions, and all of them stays within 2% of the variation of the hedge, which for the BIS requirement for hedge effectiveness, they should be between 80% and 125% of the changes on the period. So we can see that our hedges are extremely effective, even if we trade in 11 or 9 contracts representing 200,000 cash flows. And we actually also stress test this model into different conditions. We use not only cash flows that are only positive, but also a bank that would be raising, issuing debt and at pre-fixed rates to actually fund the portfolio. We can use that in several forms. This is just one example we use. Here's a little bit of the literature that we use, a generic literature, and some of the writings of our partners at Finor. I'd like to thank you.